Hello everybody, and welcome to day 8 of climate change. Last time we were together, we talked about albedo and how a changing in the reflectivity of the Earth's surface will change the amount of energy that's able to be trapped in the atmosphere. Today, we're going to take that knowledge as well as our understanding of the greenhouse effect and other atmospheric processes and combine it together and understand a little bit about how we can make predictions of the future using climate models. Come on along. Our quote for today comes from actor and former governor of California, Arnold Schwarzenegger, who says, "I've starred in a lot of science fiction movies, and let me tell you something. Climate change is not science fiction. This is a battle in the real world. It is impacting us now." We are going to continue with our understanding of what is required for a stable energy budget on Earth, and we are going to apply that to climate modeling. So to get started, I want to take a look at a simple model of the carbon cycle, which is a component of our climate system. And so if we look at this drawing of the model, we can see how we have carbon stored in different locations on Earth. And we can see that we have carbon is being transferred between these different locations. And we are going to call any place where carbon is going to it more than carbon is coming from it, such as the ocean, a carbon sink, and any place where we have more carbon going from it than to it, a carbon source, such as fossil fuel emissions. And so let's take a look at the ocean as our first example. If we look at this, we have 92 billion tons of carbon exiting the atmosphere and going into the ocean every year. We have 90 billion tons of carbon exiting the ocean and going into the atmosphere every year. But while the ocean is losing 90 billion tons of carbon every year, it's also gaining 92 billion tons. And so if we want to think about the effect of the ocean on moving carbon around in the carbon cycle, we can think of a 2 billion ton net movement into the ocean sink. If we look at how terrestrial vegetation plays a role, in the winter and during decay, plants respire and give off carbon dioxide to a tune of 60 billion tons of carbon a year. You're thinking, that's a lot. Well, it is a lot, but plants are also absorbing 61 billion tons of carbon a year. And so the terrestrial vegetation serves as a carbon sink that is storing 1 billion tons a year. Then we've got fossil fuel emissions. Well, we're not creating much oil and natural gas and coal right now, but we are burning it. And so we are seeing that that is kind of a one-way source of carbon in the atmosphere. And so if we look at our system, we've got about 6.5 billion tons of carbon entering the atmosphere from fossil fuel emissions and changes in land use. And this changes in land use is things like differing agricultural practices and deforestation and the like. And so we're putting 6.5 billion tons of carbon into the atmosphere a year, but we're only pulling out 3 billion tons. And so we can do a little bit of simple subtraction, and we can find out that over time the amount of carbon dioxide in the atmosphere is going to go up. The last thing that I want to point out here before we move on is just because carbon leaves the atmosphere doesn't mean it's not a problem. Putting carbon into forest and into soil structure tends to build up ecosystems, and we can think of that as being a good thing. But when we dissolve carbon dioxide into the ocean, while that does reduce the concentration of carbon dioxide in the atmosphere, and it helps with the climate change problem from a temperature and energy perspective, it exacerbates or makes worse the other carbon problem, which is ocean acidification. Because when you dissolve carbon dioxide into the ocean, it reacts with the water and forms carbonic acid. And we'll talk a little bit more about that other CO2 problem in the next unit when we spend some time talking about all of the different reactions that occur when carbon dioxide enters the water. Okay, let's look at another model. Here we've got some data on the left. You've seen this before, and in class 10 we're going to talk about the article from which this graph originally came, and we're looking at how over time carbon dioxide concentrations are going up. So we can see that today, or as close to today as this graph goes, carbon dioxide concentrations are around 400 parts per million, and if you go back to the beginning of the data set, they were at about 315. So there's some data for you. What's causing this increase in carbon dioxide? Well, let's take a look at the model on the right. If we look at the model on the right, we can see what the atmosphere was like in 1870, which is kind of when we're starting to think about having this type of data available, and what the atmosphere is like in 2013. And of course, if we go forward till today, you're seeing it being closer to 400 or 410 parts per million. So how did we get from here to here? What caused this increase? Well, we can break it down and actually look at the different components of the system that are causing an increase in that carbon dioxide. We've got the burning of coal, which was a big component of the Industrial Revolution, and we're seeing that at least in the United States, the amount of coal that we're burning is decreasing dramatically because of changing economic incentives. We've got a component of it that comes from burning oil. And we can use this, we can think about this as being used primarily for transportation, some heating. We've got a component that comes from burning natural gas. This is where most of our coal usage has shifted towards, as we tend to no longer produce as much of our electricity from coal. And we've got a component from cement production, and then of course the land use changes that we talked about on the other slide. And if we add all of those up, we get a concentration of carbon dioxide in the atmosphere that's way higher than what we actually see. So where did that carbon dioxide go? Well, some of it went into the land, and some of it went into the ocean. And if we add all of these up and subtract all of these, we get our concentration of carbon dioxide in the atmosphere today. And so this is an example of a simple model of the climate in a static form. So this is kind of a static model of where we are right now. If we want to understand how the temperature on the Earth will change as a result of these things, we need to look at this idea of radiative forcings. And if we can understand radiative forcings, we can understand how much our temperature will change based off of physical drivers of climate change like carbon dioxide, methane, halogens, and other gases. The change in the surface temperature of the Earth is equal to how sensitive the climate is to change times how much we're changing the radiative forcing of Earth. Now, there's a couple of words that you might not recognize. And energy hitting the surface of the Earth can be measured in watts per meter squared. And if we take the difference between the watts per meter squared coming in, the insolation, and we subtract that from the watts per meter squared going back out to space, we get a radiative forcing. How much additional energy, or how much less energy, is reaching a specific location. So if we look at carbon dioxide, we can state that the addition of carbon dioxide that we have put into the atmosphere has contributed just under 2 extra watts per meter squared over the Earth's surface. The amount of methane that we put into the atmosphere has contributed about 1.1 additional watts per meter squared. The halogens, so the chlorine and fluorine that came mostly from refrigerants, are contributing 1/3 of a watt per meter squared. And then, of course, we've got other substances such as aerosols, soot, dust, particulate matter in the atmosphere. And we see that some of them actually have reduced the amount of energy that have reached the surface, or that additional energy that's able to be absorbed by the Earth and its atmosphere by about half a watt per meter squared. And so if we take all of these and we sum all of these up, humans have caused a net increase in energy reaching the surface of the Earth and in the atmosphere of about 2.3 additional watts per meter squared. You'll often hear about how this is mostly a human-caused problem. Well, here's the human component, and here's our natural component. So what do we do with this increase in energy in watts per meter squared over the surface of the Earth? Well, we can actually take that and we can find out how much that's going to warm up the surface. All we have to do is take that number and multiply it by the climate sensitivity parameter, which has been estimated by a whole bunch of different places, and it's somewhere around 2.3 watts per meter squared per Kelvin. And if we do that, we can add all of those up together, or multiply those together, and we can get a change in the surface of the Earth. And so long as this number is above 0, Earth warms. If this number is below 0, Earth cools. And if this number is at 0, then the temperature of the Earth remains constant. Of course, you'll look at this graph and you'll see, well, there's a lot of error there. Look at the size of these error bars. This is our uncertainty. We don't know exactly where this is. It might be here, it might be here, it might be here. But we are 95% certain that it's not here, or here, or here. So, what is this uncertainty from? What causes it? I want you guys to be ready to discuss that in class based off of the reading you did for today's class. What actually matters? If we're looking at what's causing these radiative forcings to differ from 0, or changes in radiative forcings to differ from 0, what matters? Well, changes in the sun matter. Of course, we just saw that those were pretty negligible. And of course, we also can't do anything about that. The things that matter to us are things that change reflection, or albedo, and things that change absorption. For the most part, from a planetary scale, we are changing this. And of course, yes, we are changing the reflectivity of surfaces in cities and such, and the change in albedo in the Arctic is indirectly caused by us. This is what we are directly able to change. And so if we change the amount that gets stored in the atmosphere by changing absorption, we will change that radiative forcing, and therefore change the temperature. Let's take all this and let's put this into a model, a climate model, and well, we're going to talk a little bit about a comprehensive climate model. Because when we talk about models, we can mean radically different things. This can be a schematic or description of a system. We saw a schematic model of the carbon cycle. It can also be a physical object. You can make a model of an airplane. These tend to not be what we're talking about so much when we're talking about climate models overall. What we're normally talking about is numerical experimentation, a spreadsheet. This is the data that we know. These are the rules that govern it. These are the equations for that. What happens? And those are what we're generally talking about when we talk about climate models. And so if we're to build a climate model, we have to look at the entire Earth system, which is composed of a couple different spheres. We've got the ocean, we've got the land, we've got the atmosphere, we've got the cryosphere. And within each of these, there's all these different components, and you build all the different components of how the ocean works, and you build all the components of how the atmosphere works, and you build all the components of how the cryosphere works. And you take that along with the land, and then you connect all those components together. And once you've done that, you can make predictions about what's going to be the output, or what's going to happen as a result of what goes in. And so long as your understanding of the physical laws are sound, of thermodynamics, as long as your initial conditions are sound, what is it like today, you should get a good outcome. What goes into our understanding? We've got observations, which we talked about. Those are observationally or experimentally based. So these are things like, what is the concentration of carbon dioxide in the atmosphere? What is the temperature of the ocean in different locations? What is the state of the cryosphere? There are physical laws, thermodynamics, Newtonian physics. And we take those two things, we combine them together, and we use computer models to help us gain understanding. So the computer's not doing anything magical. The computer or the computer model is just helping us combine the physical laws with our observations. What is happening now with how things behave, so we know what's going to happen. And we get an output. And we can see that this is an output of a computer model. This comes from the IPCC. And this is showing, based off of what's happened in the past, here's the last 1,000 years, what we can predict will happen in the future. And the first thing we notice is there's a lot of uncertainty, a wide range of possibilities for all these different scenarios. And this wide range of different possibilities is from the third cause of uncertainty in a climate model, which is our uncertainty of what people are going to do in the future. If we understand completely how the climate system works, and we understand completely what the initial conditions are, the outcome is going to be radically different if we stop burning fossil fuels tomorrow, or if we accelerate our consumption over the next 100 years. And so when we look at our uncertainty in the climate model system, the biggest cause of uncertainty that we have is not caused by not understanding how climate works. The largest cause of our uncertainty is we do not understand what humanity's actions are going to be. And so in the outcome of what's going to happen with the climate, the largest factor contributing to what happens is how we behave. And if you look in the IPCC report, you can actually look up these different scenarios, and you can state, like, what are the conditions? These are how humans behave. So if business as usual, we take no steps to mitigate our climate impact, this is what we get. This is the dramatic systemic worldwide action where all nations get together and work to solve the problem. So we can actually state, if people do this, this is what the result can be expected to be. You've seen this graph before, or this figure before, and this is from the IPCC report, scenario B2. And so we can actually look on our graph. Here's B2, it's the blue one. And this is our middle of the road warming. This is, we take some actions, but they're not systemic worldwide actions. And we result in a planet that looks like this. And based off of our model, we can make predictions about where it's going to get warmer and where it's not going to warm that much. And of course, it's warming more at the poles than at the equator, because the Earth and the atmosphere and the ocean acting like heat engines. We're taking all the extra heat from the equator and we're dumping it into the poles. And this is an outcome. And so we've taken that numerical model in a spreadsheet, and we've made a pictorial representation that hopefully provides some meaning or insight to us. So, what do we do about all that? What is our framework for interpreting the models, or for looking at the different scenarios? And this has to do with what our response is. And our response is comprised of two components: adaptation and mitigation. So when we talk about adapting to climate change, this is how we're responding to changes that occur from added CO2. So these are types of things like building seawalls, rising roads, installing air conditioning in places that haven't had it before. That's adaptive. This does not prevent the problem from getting worse. This just is how we deal with worst problems that exist. The other component is mitigation. And this is where we control the amount of warming that occurs. This is where we are reducing the amount of carbon dioxide we're putting in the atmosphere, or controlling that amount, or changing the reflectivity of surface, or any of those other things that we're doing to reduce the impact. And our response is not an either or, it's a both and. We are adapting to climate change in certain parts of the country and the world already. And we will have to mitigate the amount of CO2 that we put into the atmosphere. So how does it work? Well, climate changes, temperature rise, sea levels rise, precipitation changes, you get floods and droughts and fires and storms, and we adapt to those. And when we adapt to those, that changes our food and water resources, it affects our ecosystem and biodiversity, it affects human settlements with migration and disease and our general health. And because of these changes, we have to adapt, and this impacts economic growth and technology and populations and how we govern and interrelate with other people. And because we want to avoid having to deal with this, we mitigate the problem, so we try to reduce the amount of CO2 we put in the atmosphere. So we're controlling our emissions, concentrations of CO2 in the atmosphere, greenhouse gases, aerosols that we're putting up. And that should reduce the amount of climate change that occurs. So the more of this that we do, the less of this will have to happen. One of the goals of this class was to get you building climate models so that we can kind of understand what they do. And so I have found this little program for you to work on through Coursera. You can just click this, it's a link. And you create a climate model using Python, which you learned in freshman technology class. This is class Global Warming 2. You don't need to do Global Warming 1. You already know everything that's in that class. And so you can skip to doing this. So what you're going to do is you're going to sign up. And you're going to work through this. And you can work with a partner. And you just need to make sure that you complete it by test day. As you model, it's important that you follow energy through the Earth's climate and how it's transferred around. How does it get from outer space? How does it get absorbed by the surface of the Earth or reflected? What happens to it when it's re-emitted? How does it get back out to space? How does it move around? We have to follow that energy through because the Earth system is not just a point. It's not just a place that has a temperature. Just the average temperature of the Earth is not enough. If it was, the idea of having a 1.5 degrees of warming wouldn't be that big of a deal. But it's actually what that extra energy is doing. Energy can be stored as thermal energy in that temperature, but as it is moving around, the energy can also be stored in energy of motion, wind and water movement. And this actually tends to be what we think about right now as a lot of the impacts that we're seeing with climate change today. And so we cannot ignore the energy that's traveling around and redistributing itself, not just as temperature. We did a lot today. We're going to slow down, we're going to take a couple days, and we're going to focus just on our modeling. And so as you build your models, hopefully it will help you gain an understanding of what climate models are and how they work. And with that, I'll be here along the way to help you through the process. I hope you have a good day, everybody. Bye-bye.